Thank you for the opportunity to speak to you about carbon capture and storage. And during my presentation, I will first spend some time on the energy trilemma with a European perspective. The energy trilemma calls for the need to manage both energy security, affordability, and decarbonization at the same time. And in this context, I will take you through some thought experiments to illustrate the scale of the challenge with the energy transition. And I hope all this will serve as a backdrop to why Equinor is not only investing massively into renewable energy, but also into a broader toolbox in our energy transition. And this broader toolbox very much includes CCS, carbon capture and storage. And then towards the end, I will give you a flavor of some of our projects and also point to the importance of bringing CCS to commerciality. So I hope you're ready for that. And then let me start with drawing your attention to this figure. It shows the price development of natural gas from early 2021 and to the end of April this year. And the price development is also a reflector of the energy crunch last year with a cold winter. And then later, the Russian invasion of Ukraine, which made it even worse. And when we look at this period, we can observe that the focus of the energy trilemma has shifted 3 times. So in the first period, the CO2 footprint of the energy system was on the top of people's mind. And decarbonization was by far the part of the trilemma getting the most attention. And in this period, there was actually high volatility in gas prices, but you can hardly see it because of the next period. And in the next period, gas prices are increasing rapidly. Volatility starts to get more extreme, and the focus of the trilemma shifts towards energy affordability. This is now on the top in the public debate and among the politicians. So just a few reflections, why did we experience this rapid price increase and this energy crunch? And when we look back, we can see there are several factors into play. First of all, it was a cold winter, a long winter, not a lot of wind. And this was also combined with less gas exported to Europe, but going to the Asian market. So this impacted the energy storage level needed for the winter seasons. But then again, seasonal changes is something we are quite used to tackle in the European system. And the changes we saw this winter, they were not really that dramatic. But what is new is the result of intermittent sources from solar and wind, which has been added to the grid. And when you have more intermittency, you also need more energy storage to balance. And although need for energy storage to balance intermittency has been addressed as an issue previously, it was really now becoming firm and realities and on top of the agenda. So both the energy affordability and issues related to intermittency is now in this period the focus in the trilemma. And then we came into the third period, a dark place in our history with the Russian invasion of Ukraine. And at this point of time, security of supply became and still is the #1 topic in our energy discussion in Europe. So we can observe how the focus in the energy trilemma has shifted 3 times during a relatively short period. And in the current situation, it may be tempting to regard decarbonization as a more longer-term issue, something we can fix later. But we cannot allow ourselves to do that. The latest IPCC reports conclude code red on climate. And the energy transition is going too slow. We must speed up, and we must have action at scale to achieve the necessary decarbonization. And I will also spend some minutes now to illustrate this scale of the challenge with the energy transition. So the first figure here shows how different sources of energy has come into play in our energy system, the global energy system, in a 200 years perspective. So the steep increase in all the energy sources tells us that the new energy added has never replaced the old energy sources. So the new energy sources have covered for the increase in demand from a growing population, from a society that is using more energy as more people is getting out of poverty. And the figure also shows fossil fuel is dominating the energy system. And that is a fundamental challenge. Because when you use fossil fuel, CO2 is emitted. So why is it that dominating? And one of the explanations for that is that fossil fuel has the advantage that it can store and it contains a lot of energy. And this energy, you can basically relocate it to where you need it. You can use it when you need it. So it's different with renewable, such as solar and wind, which generate electricity. Because electricity has to be used when it is generated. It doesn't store energy itself. So if you want to store electricity, you need a battery. But then there is a limitation on how much energy you can store in a battery. Let me give you just a simple example to illustrate the energy content of fossil fuel compared to electricity generated by renewable. If you have one ship loaded with natural gas, it contains the same amount of energy as a whole year of production from Equinor's offshore wind farm, Sheringham Shoal. And that is a pretty large wind farm. It has 88 turbines and it provides power to 280,000 British homes. So one shift the same as a whole year of production. And if you think about that, and again look to the figure to the left, towards 2050, all of this must become clean. It means that coal, oil, and gas must either be electrified or decarbonized. That is a massive challenge. And I will look into some thought experiments just to illustrate what a massive challenge this is. So the first thought experiment, we are concentrating on the energy system in Europe here. And in this case, we will look into what will it take to replace the sector's nuclear, coal and gas that is currently fueling the European energy system. And again, this is a very simplified illustration and we have left the current oil products out of the equation for now. So we want to replace nuclear, which is debated in Europe at the moment, and we want to replace coal and gas. And the energy content from these three sectors amounts to 8,500 terawatt-hour a year. And that's a big number. It's quite hard to understand, so I'll try to break it up a little bit. So in this case, we will assume that the 8,500 terawatt-hours is replaced with new renewables and with green hydrogen. And we need the green hydrogen as the energy storage to balance the intermittency from renewable. And that would imply that we need to build a lot of new projects. We need to add 4,800 gigawatt to the grid from new renewables. And in addition to that, 790 gigawatt dedicated to green hydrogen. It's still a bit hard to grasp, so we will look on what it will take in terms of investment. So to build all these projects, we would need a yearly spending of 10 trillion euros. And what is 10 trillion euros? It's a big number. It's the same number spent on oil and gas investment globally the last 25 years. And it's also comparable to 310 times the yearly spending on renewable in Germany during the energy Wende. And then we can look at the lead time of delivering these projects, looking at the supply chain. And if we assume that we base it on the current supply chain in Europe today or in the world today, it will take 100 years to get there. And as we know, there is less time available towards 2050. If we then look at the land that will be required to install these new renewables, the estimation is 353 square kilometer, and this is about the size of Germany. So I guess the number speaks for itself here, that this is not a feasible solution. We need more tools into this equation. Then let's look at the next example. And in this case, we keep the debated nuclear in the energy system, and we concentrate our effort on replacing coal and gas. So there's a little bit terawatt hour to be replaced in this example, 6,300. And this time we replace it with new renewable and nuclear. We assume 50-50 by each. The investment needed in this case is 6.6 trillion euros, still enormous, but lower than the previous example with 10 trillions. We need 242 nuclear plants. This is equivalent to the nuclear that exists today globally. And if we look at the lead time for these nuclear plants, which is a challenge, and we assume China level, which imply commissioning 4 new nuclear plants each year, it will actually take 68 years to install these 242 reactors. And the last thought experiment is the same as the previous one, but in this example, we look to replace coal and gas with new renewable and blue hydrogen. And to produce blue hydrogen, we are reforming natural gas to hydrogen, and we combine it with carbon capture and storage. And this, thought experiments would lead to the need to store 1 gigaton of CO2 every year. That's a lot. Still, if you look at the North Sea, there is capacity for more than 100 gigatons. So in theory, we could store this amount for 100 years. The investment required for this thought experiment is the same as the previous example, still very significant. And in terms of number of hydrogen plants that we would need, it's about 40 mega blue hydrogen projects. So that is also still significant. So my point with this illustration is not to bring one technology against the other, and it's not to paralyze ourselves. It's quite the opposite. It is to illustrate the scale of the challenge, to point to the sense of urgency to take actions at scale, and to bring realism into discussions by looking at feasibility when we address the challenge. And when we are doing this, it should be recognized that a broader toolbox must be used, and every technology and solution that can deliver in a sustainable way must be used. So with this backdrop, Equinor, we have announced that we want to become a net zero company by 2050. And this implies that we are addressing both the scope 1 and 2 and 3 emissions. And to achieve this goal, we are focusing on 3 pillars. One of them is optimized oil and gas portfolio. And our focus is to produce oil and gas with the lowest emission possible. And here we are already industry leading, but that is not enough. The second pillar is high growth in renewable. And the third pillar is low carbon solution. And low carbon solution is basically CCS and hydrogen. And we have stated that by 2030, half of our investment will be into renewable and low carbon solutions. Our low carbon solution project is addressing the energy intensive part of the energy system, the part that are hard to abate and cannot be electrified alone. And to be more specific, we are providing low carbon solution for industrial processes, for clean power that can balance intermittency and that can manage the seasonal fluctuations, and to long range transport. And with this in mind, CCS can be used in 2 ways. You could either capture emissions from the flue gas from your industry, for example, Or you can capture emissions from the fuel before the fuel is being used by the industry or by the power plant, as an example. And the latter one is what we refer to as blue hydrogen. Again, we reform the natural gas to hydrogen, combine it with CCS. And in this way, we can produce a clean fuel at the large scale that is necessary for these energy-intensive segments. And by the way, in Equinor, we are developing both blue and green hydrogen projects. We think both are necessary. And we think that blue hydrogen has a role in making the scale we need, and pave the way for the hydrogen infrastructure that both blue and green can benefit. So in June last year, Equinor announced specific targets for CCS and hydrogen. And we state that by 2035, we will develop CO2 transport and storage capacity of 15 to 30 million tons a year. And that's the equity share. Northern Lights is one of our flagship. I will come back to that, and Northern Lights will contribute to this target. But I would like to put it in context with Northern Lights, because if you consider our share in this project and the scale of this project, it will bring us to 1.5 million tons a year. So we really need 10 to 20 times this to achieve the target. And in the same period, we've also stated that we will develop 3 to 5 hydrogen projects. And these hydrogen projects will require a fair share of the storage capacity that we are developing. And I think it's fair to say that these targets are quite bold when you consider that there is currently not a market in place. This is our portfolio of CCS and hydrogen projects. And you will notice that we have grouped them into project type and nations. We are focusing our effort in Europe. This is where we have a strong position, but we are also focusing on the US, and I'll come back to that. And for this project, the commercial framework is not in place. Our approach is still that we need to develop this project, and it needs to be, we base it on a firm and strategic belief that government and industry will shape and develop the necessary framework to make the investment. So we are developing our project first in the nation that have policy support to CCS and hydrogen, but we believe that the other nations will follow soon. And as you will notice here, both Norway and UK and US is among these frontrunners. And very soon in my presentation, I will come back to some specific projects. So when we are now scaling up CCS significantly, we are not starting from scratch. Around the globe, you will find more than 25 industrial CCS projects in operation. And the major part of these are, as you may know, in North America, and they are onshore. In Norway, we have some unique CCS projects in operation offshore. We started with CCS at Sleipner field, as you can see here on the map, in 1996. And at that time, this was the first offshore CO2 storage in the world. And even today, Sleipner and Snøhvit, further in the north here, stands out being 2 out of 3 or 4 offshore storage sites on the global basis. Sleipner and Snøhvit was really incentivized by the national CO2 tax that was introduced by the Norwegian government in 1991. And Norway was, in fact, the first country to introduce CO2 tax. And there were a lot of CO2 in the Sleipner gas, so we had to remove the CO2 to meet the specification from the customer. So we then could choose between removing the CO2 or capturing the CO2 and then emit it to the air and pay the taxes. Or we could choose to capture the CO2 and find a solution to permanently store it. And we decided on the latter one. And this was a very strategic decision that we have gained a lot from. I would also like to mention Technology Center Mongstad, together with partners, including Gassnova and half of the Norwegian state, we have been part of these unique test facilities for capture technologies since 2012, so 10 years now. And a wide range of CO2 capture technologies have been at Mongstad, testing their technology at the final stage before the industrial implementation. And from all these projects that you can see on the map here, these are really benefiting us now. And the next project that will come into operation is Northern Lights. We have made investment decisions. We did that in 2020, and we are ready to start operation in 2 years from now. So then, Northern Lights, we are building a CO2 transport and storage infrastructure that can be used by industry. So basically, industry, they can concentrate their efforts on capturing their emissions. They need to bring it to the harbor, and the Northern Lights project will collect it then by ship and bring it to Norway for permanent storage. And the construction work is well ahead, as I will show you on the next slide. And Northern Lights is also part of a full CCS value chain called Longship. And Longship is heavily funded by the Norwegian government. And there is 2 Norwegian industrial CO2 capture project part of Longship. It's 1 cement factory and it's 1 waste to energy plant. And this really ensures progress along the full value chain, from capture to transport and storage. And the industry, together with the government, is solving this chicken and egg problem. And Northern Lights is marketing spare capacity in the infrastructure. And the interest from Europe is overwhelming. So we see capture projects being matured by a broad range of industry as a consequence of this infrastructure. We see projects in cement and steel and waste to energy, power and bioenergy, and even direct air capture. This is a graphic on what it will look like when it comes to operation. So the ships will come from the industry in Norway and Europe. They are loaded with CO2. It will come to the receiving terminal, and the CO2 is transferred to the storage tank that you can see here in the back. And there the CO2 is stored intermediately, and then it's transported through a pipeline for permanent offshore storage. And this is how far the construction work has come. So only 2 years from now, we will be ready to receive the first ships. So I mentioned that the interest from industry is overwhelming. And the figure here illustrates that the potential customers that Northern Lights is in dialogue with is more than 10 times the capacity of the pipeline from the receiving terminal to the permanent storage. So you can really indicate that the Northern Lights is oversubscribed, and there is the need to develop more CO2 infrastructure for the European emitters, and we need to do that fast. And we in Equinor are already on that task. So we were thrilled when the Norwegian government just recently announced the award of 2 new licenses to Equinor on the Norwegian continental shelf. And one of them is named Smeaheia. And we believe Smeaheia has the potential to store 20 million tonnes a year. And with this large storage capacity, we are now looking into establishing a pipeline from continental Europe to transport CO2 to the Norwegian continental shelf and to Smeaheia for permanent storage. So introducing a pipeline instead of ship can significantly reduce the cost and make CCS a cost-efficient decarbonization method for the European industry. And as you also can see here, when we are scaling up towards our target, we are building on the experience from Sleipner and Snøhvit and from Northern Lights. And then I would like to move to another important project, and this one is in the UK. This project is referred to as the East Coast Cluster. And this is a CO2 transport and storage solution that is serving 2 industrial clusters in the UK named Teesside and Humber. And if you look at Teesside and Humber, they stand for 50% of the industrial emissions in UK. And this East Coast cluster is designed with 2 pipelines, as you can see here on the figure, one from Teesside and one from Humber, and ending up in an offshore CO2 storage named Endurance. And the system here is designed with a capacity of 27 million tonnes a year. So with the high CO2 emissions from this industry in Teesside and Humber, we can really make the case for a pipeline rather than ship. And this is bringing down the CO2 transport and storage cost unit considerably. So there is a significant economy of scale with CO2 transport and storage. And what I really would like to highlight with UK is UK's commitment in the energy transition. It stands out in a European perspective, and I think also in a global perspective. And it's driven by UK's legal commitment to reach net zero by 2050. So in UK, the government has provided the so-called 10-point plan, which is a tool to deliver on this energy transition. And CCS and hydrogen represent 2 out of these 10 points. And specific targets are stated. If we look at CCS and hydrogen, it's stated that 2 CO2 transport and storage clusters shall be in place by the mid of 2020. So that's not far from now, and further to by 2030. And the aim is to store 30 million tonnes a year by 2030 and 50 million tonnes a year by 2035. And on hydrogen, the UK government have a 10 gigawatt target by 2030. And then to incentivize industry to deliver these projects and progress this project, government is running competitions. And in the last 2 years, the so-called cluster competition is ongoing. And this is about prioritizing which are the first CO2 transport and storage infrastructures that will get government support. And our East Coast cluster was among the 2 selected. And this was a significant milestone for us. And the next part of the cluster sequencing is selecting the emitter project that will get support from government and that will get the first access to the transport and storage infrastructure. And Equinor, we are part of both the CO2 transport and storage infrastructure and specific emitter project that seek to connect. And we are part on projects, or we are leading and developing projects on hydrogen and also on post-combustion power project, all designed to decarbonize industry in Humber and in Teesside. In parallel with the targets, with the competitions, with the funding opportunities, government is also working hard on business model that will be necessary for the investment decisions. And at times they are having weekly meetings with the industry and engaging to look into how risk can be shared. So as you may sense, I really think UK is leading the way in Europe on the energy transition and to ensure the opportunities related to CCS and hydrogen in terms of decarbonizing. I mean, the UK government also recognize what it can bring in terms of protecting existing jobs and also to bring new industrial opportunities fit for the future. So then the last project I would like to mention for you is our US project, the 3-state project. And the name is given due to the architect of this clean hub, which spans across 3 states, Ohio, Pennsylvania, and West Virginia. And in this project, we are bringing learning from the UK projects that I just talked about, which means that we are taking an architect role and evaluating how we can develop a clean energy hub in this area based on hydrogen and based on CCS. And we are not in the 3-state by chance. It has many of the same building blocks as we find in Teesside and Humber. There's a lot of energy in the area, a lot of heavy industry emitting CO2, and a lot of CO2 storage potential. And on top of this, we as a company has an important asset here, a gas asset in the Appalachian Basin. And we want to leverage on that. So this slide illustrates how an energy hub could start and how it could look like. So first of all, we need a gas reformer to reform natural gas to hydrogen. And the CO2 in this process must be captured and transported to a storage site. And a CO2 storage site will be developed with the view to store CO2 from several emitters. So a CO2 trunk line is needed to bring the CO2 from all these emitters and to the storage point. And then the hydrogen pipeline showed here transport the hydrogen from the gas reformer and to the industries that want to switch to a clean fuel. So based on the gas reformer producing hydrogen, the storage site that can take the CO2 from the emitters and the low carbon infrastructure, the industry in this area can decarbonize, either by capturing their emissions and deliver it to the CO2 infrastructure or by switching fuel to clean hydrogen. And over time, additional industries can add and connect to the infrastructure, and additional hydrogen capacity can be added, as well as additional CO2 storage sites. So we believe there is a significant potential for decarbonization in this area once the infrastructure and policy framework is progressing. So based on our projects, we observe a strong momentum for CCS. But despite this, I have to emphasize this is not a walk in the park. There is today a commercial gap between what it costs to implement CCS and what it costs to emit the CO2 and pay the taxes. And that goes for Europe as well as for US. And the figure to the right-hand side illustrates this. You know, the gray bar here shows the cost range of CCS today. It's not one cost for CCS because it varies with the industry and how much CO2 is in the flue gas and what kind of CO2 transport solution is available for the specific industry. But the range is as indicated here on the slide. And then the red dot shows the EU ETS price, the cost of emitting CO2 in Europe. So currently you can see the gap is very evident. The EU ETS price has been quite volatile since June 2021, but we believe in a perspective towards 2030 that it will be around 100 euros per ton and still rising. And in this same period towards 2030, we also expect the cost of implementing CCS will come down. And this will be a result of economy of scale, of industrialization and technology improvement. And then perhaps around 100 euros per ton, the cost of implementing CCS will break even. But to get there, we really need the help from the initial wave of CCS projects. They are the one paving the way and are the front runners and the pioneers. So to make this first CCS project happen, there needs to be a close collaboration between the government and between the industry, just as we see in the UK as an example, and that we also are seeing in the US. But this needs really to be stepped up even more. So then finally, I'm just summing up my key messages of today. Remember, a code red for climate. That means we must act accordingly. And the investment in the energy transition must speed up. There is really a sense of urgency. When we look at the scale of the energy transition, it's massive, and we need to use the broad toolbox. And CCS is an important part of that toolbox. All scenarios modeling points to the need of significant use of CCS. So if we are serious about net zero, we must invest in CCS. Industry, we are mobilizing projects, but we need clarity on the policy framework to ensure progress and investment and the growing number of CCS projects. And finally, CCS is an opportunity for efficient decarbonization of the energy-intensive segment. It brings industrial opportunities as well as it is protecting existing workplaces. So with that, I would just like to thank you very much for the attention.